Okay, so this is the second part of chapter 4, and we're going to start with electricity and magnetism. I apologize for making this so broken up, but it is a very long chapter and a whole lot of information. So just bear with me, and hopefully this one will make a little more sense. So now that we've talked about the basic principles of electricity, specifically electrostatics and electrodynamics, let's move into magnetism. Now, electromagnetism is electricity and magnetism as two different parts, but they come together as electromagnetism. And it is the relationship between the two of these properties. Now that you already know that electricity is electric charges in motion, now let's talk about magnetism. Magnetism is the ability to attract iron, cobalt, or nickel. And by doing that, another way of defining it is a force field created by moving electric charges or electric currents and magnetic dipoles. So it exerts a force on other nearby moving charges and magnetic dipoles. A current that flows through a conductor creates a magnetic field around the conductor, and that strength of the field increases with increased current. And let's start. So again, the magnetic properties of cobalt and nickel assume their pure form. Magnetism is the ability to attract iron, cobalt, or nickel. The U.S. nickel, a coin that you use, does not actually have a lot of magnetic properties because it's only 25% nickel. The rest of it is copper. Iron is relatively abundant and used extensively in the creation of magnets and magnetic fields. Now, why do I throw in that the actual nickel doesn't have a lot of magnetic properties? Well, that's because really none of our money does. I mean, they've changed it. You know, we used to have silver coins and now we've diluted it to other materials. But you couldn't use iron because iron is so heavy, then we wouldn't be able to tote it around. So, moving forward. The nature of magnetic materials is such that the orbital electrons of their atoms spin in predominantly one direction. Those atoms create tiny magnets called magnetic dipoles. When these dipoles or atomic magnets form groups of similarly aligned atoms, they create magnetic domains. And these domains exist in magnetic materials. Okay? But they're not coordinated with one another. When such magnetic materials are placed in a strong magnetic field, the domains align with the external field, which then organizes them and magnetizes the material, which creates a magnet. Conversely, an electric dipole is two charged objects with equal but opposite electric charges that are separated by distance. So that's what's the difference here between electricity and magnetism. So the magnets align with the external field and magnetizes them to the material. A magnetic field consists of lines of force in space called flux. And they have three basic characteristics. So the first characteristic I'm going to talk about here is that lines of flux travel from the South Pole right there, to the North Pole inside the magnet, and from the North Pole to the South Pole out here. So this is showing you from here to here it's going inside, and then here to here is on the outside. And that creates these elliptical loops. So that image is from your book, and it's the lines of force in space called flux. So that's our first basic characteristic. Okay, they travel south to north inside and north to south outside. Okay. The second one is that lines of flux in the same direction repel each other. Same direction repel. Lines of flux opposite attract, just like your regular electrons, protons, and all those good things. Like things repel, opposites attract. And then the third characteristic is that magnetic fields are distorted by magnetic materials but are unaffected by non-magnetic materials. Whew, that's a lot, but you need to know these three basic characteristics. And it started over here of a magnetic field. Okay, so here's one, the way they travel. Here's two, they either repel or attract. And then they're distorted by magnetic materials, unaffected by non-magnetic. There are also three laws of magnetism that may help you understand this. And maybe I should have put it first, but it comes afterwards, but it'll help you in a little bit. The first law is that every magnet has a north and a south pole. So then you can relate that to that number 1. When it goes from south to north, it stays inside. If it goes from north to south, then it's on the outside. The second law is that like poles repel and opposites attract. And then the third is that the force of attraction or repulsion varies directly with the strength of the poles and inversely with the square of the distance between them. So I'm saying basically the same thing, except the other was a magnetic field, and this is just three laws of magnetism. So just remember the definitions of them, okay? The unit of measure, or the strength of a magnetic field, is measured in Tesla, and that's the SI unit, and that was named for the American physicist Nikola Tesla. Magnetic resonance imaging, or MRI units, that we use in medical imaging are referred to by their magnetic field strength. So when you hear about, or if you ever have to go have an MRI, or once you've gotten into the program and you think that's the field that you want to go into, people look for the strength of the magnet. The higher the strength, the better the quality of the image, but they're more expensive and they're more prone to accidents, so you have to worry about that. And 0.5 to 5 Tesla. Right now, the 5 Tesla is experimental. They haven't tried that. Most of the ones that you'll see out there, they'll say a 2T or a 3T. Those are the ones that I hear more often than any of the others. Now, here's some other magnetic classifications. Now, again, we just went through over electricity, and you're going, well, why do I need to know about magnetics? Because electromagnetism, is what is going to actually affect our X-ray tube. So just as materials can be classified as conductors or insulated, they are insulators, they can be classified by their magnetic properties. 4 categories: non-magnetic materials, and they're not attracted to the field at all. Again, when I give these examples, those are not the only examples out there, but they're the ones that come to mind. Glass, wood, and plastic would be non-magnetic. Diamagnetic are weakly repelled, so that's water, mercury, and gold. And I said diamagnetic earlier when we were talking about electricity. And then you have paramagnetic materials that are also weakly attracted, so the dia are weakly repelled, para are weakly attracted, so that's platinum, gadolinium, and aluminum. So working in a department, I've had patients tell me before they didn't want to take off their jewelry because it was platinum, it wasn't, anything else. Well, that's good and fine, but you still don't want it in there, because if it's weakly attracted to the magnetic field, what it's doing on your hand inside that magnet is it'll just move around and around, and it could still create a burn because it's weakly. Now the ones that are gold shouldn't, it's repelled, but it could still cause a problem. So when you get to MRI and you get in there, and you'll see what I'm talking about, people for some reason just do not want to get undressed and put on a gown, and you have to remind them why, but irrelevant to this talk. Okay, and then you have ferromagnetic materials that are strongly attracted to magnetic materials. So iron, cobalt, and nickel are the ones that are most attracted. So you need to know those 4 types. And just know, non-easy, not attracted. And ferromagnetic is just another way of saying iron, so it's very much. Your dia and your para. So if you have a dia, that means I'd rather die than go close to you, so you're repelled, however you want to remember them, but just remember what each one of them does. Now that we've talked about electricity and magnetism, now we can discuss them together as electromagnetism. And that is any flow of electrons, whether in space or in a conductor, anything is surrounded by a magnetic field. Likewise, a moving field can create an electric current. Okay? So when you have a flow of electrons in electricity in a conductor, you will automatically create that magnetic field. And when that magnetic field moves, it can create an electric current. And that's how these two are put together. The principle of electromagnetism was first identified by the Danish physicist Hans Ørsted when he discovered that the needle of a compass is deflected when placed near a conductor carrying electric current. So that's how they determined that. It was later discovered that the magnetic field surrounding the conductor could be intensified, so they could make it stronger by putting it in a coil, and that's where we got the word solenoid or solenoid, however you want to say that. You could further intensify in it by adding an iron core, and that's an electromagnet. So originally, the needle of a compass is deflected when it's close to a current. And then if you coil it, it'll get even stronger. And then if you put an iron core in the coil, then it becomes an electromagnet. So that's where we get electromagnetism. These two things work well together. Shortly after Ørsted's discovery, British scientist Michael Faraday found that moving a conductor, like a wire, through a magnetic field induces an electric current in that conductor, and that is called electromagnetic induction, right there. Fashioning the conductor into a coil, passing it through a magnetic field increases the induced voltage, and that voltage will increase with an increased number of coils. Increasing the strength of the magnetic field or the speed with which the conductor is passed through the field increases the induced voltage. And that's the powerful electromagnet which we use in radiographic equipment. So not only is it useful in the X-ray tube for the electromagnetism, but this is what actually creates our MRIs. Now this is not an MRI study, but eventually you'll need to know that Michael Faraday was credited with the discovery of using magnets to make an image. Two forms of electromagnetic induction are used in the operation of the X-ray machine, and those are mutual induction and self-induction. Mutual induction is the induction of electricity in a secondary coil by a moving magnetic field. So you have to have another field and then the two will work together. So mutual. Self-induction is a bit more complex, but it involves the changing magnetic field. So if the field itself changes, it can like self-propel itself or self-induction. That's the difference. So this is a picture of mutual induction. This image is in your book. The coil on the left is connected to an AC source right here. As we talked about earlier, a magnetic field is associated with the flow of electricity, and the alternating current, or AC, switches direction of flow in cycles. Each time the AC switches direction, the associated magnetic field also changes. That is, the north and the south fields, or south poles, of the field are directionally oriented to the flow of the current. So when the current changes direction, the previous magnetic field dies away and a new one is created, and it's in the opposite orientation. And this is the important part of this, is that it's called a moving magnetic field. So this is moving. That's how this happens. The previous field collapses, a new one expands, then current changes direction again, process starts all over. And when this moving magnetic field is placed near a secondary coil, and that's this one, then it's induced to flow in that coil. And that's also alternating current because it will also switch with the change in magnetic field. So This one can work on its own and it creates a movement, and then you put it near another one and then the electricity is moved into that coil. So that's what mutual induction means. Self-induction is a bit more complex, so that you need to understand something called Lenz's law. It states, an induced current flows in a direction that opposes the action that induced it. So in this case, that action is the changing magnetic field. And if you return to the example of the primary coil, that one, then the magnet is created in this coil and expands outward from the center of the coil, okay? And as it does so, it cuts through the turns on the coil, and that act of cutting creates a current within the same conductor that opposes the original. That is all Lenz's law. And using direct current, this phenomenon is short-lived because the magnetic field reaches its max and then the cutting action stops. But when you have alternating current, it just continues going on, and then that's where you get that fluctuating magnetic field back and forth through a single coil. And this is what is self-induction. This self-induction is important because it is used in the auto transformer. Now, I don't have it on this slide, but we're going to talk about the auto transformer in just a second. Okay? Here we go. When it comes to electrical equipment, electromagnetism and electromagnetic induction have many applications. And of particular interest to understand the X-ray circuit, we need to know what a generator, an electric motor, and a transformer is. So let's go through each one of these individually. So you need to know the difference between these three things. An electric generator is a device that converts some form of mechanical energy into electrical energy. So there you go, generate. Converts mechanical to electrical. Here's a mechanical input of a hand, and we make it moved, and then it becomes an electrical output. And that is some of the first electricity that we got. Some examples of that is the force of water through a dam, and so when that happens, that water actually turns it into electrical energy, created by burning some type of fuel, turning a turbine, or the wind in a windmill. So all of that can just be created by something else. But in its simplest form, which is what this picture is right here, a loop of wire and a magnetic field induces a current in that loop, and that's electromagnetic induction. And then when it cuts the magnetic flux line, when the loop cuts the magnetic flux lines, a current is induced. The more complex uses coils of wire with an armature that's rotated in a magnetic field by some mechanical means. Bottom line is, a generator generates some type of mechanical energy into electrical energy. So kind of keep that in mind right there. Now, motors and transformers. An electric motor is a device that converts electrical energy back to mechanical energy through electromagnetic induction. In a simple motor, an armature is placed in an external magnetic field and is supplied with alternating current. Every flow of that current has an associated magnetic field. Then that magnetic field is oriented so that the north pole is next to the north pole of the external field, and the south pole is next to the external south pole. Because they repel, the armature flips to orient itself to the external field. And at that same instance, the two magnetic fields align, the AC current changes direction. A new magnetic field is created, it's not aligned, and then it rotates again. So this is a continuous movement converting that electric energy to mechanical energy. And a more sophisticated variation is the induction motor, which we've already talked about when we went over chapter 5. Okay, so in a motor that converts it from electrical to mechanical. So here we had to have a generator to create that electrical energy. Now we're using that electric motor to convert that electric energy to mechanical. So when you have a generator, pretend like your lights went out and your plug in the wall doesn't work, but you can have a generator that runs on gas creating electricity, well, now your plugs will work and you can then have mechanical energy again. And then what's a transformer? A transformer is a device that's used to increase or decrease voltage through electromagnetic induction. Okay, so the transformer changes the voltage or the current. So you have to have a generator to create the electricity. The electric motor takes that electric energy and makes it into mechanical energy, and then the transformer decides, do I need more power or less power? So a transformer, they're named for their effect on voltage. Now we're kind of back into X-ray talk, but a transformer can work in any type of electrical situation. A step-up transformer increases voltage. A step-down transformer decreases voltage. And then you need to know that the change in voltage is an inverse relationship. As voltage is increased, current decreases. But if we decreased our voltage, then the current increases. What does that remind you of? The kV 15% rule, and then maintaining intensity of an X-ray? Well, this all works in just an electrical situation also, okay? So that's how this all works. Interesting, isn't it? Transformers are named. Note that the expressions assume ideal circumstances in a transformer and do not take into account. So some of the considerations, let's go back to here, what a transformer is. It's named for their effect on voltage. So that is ideal circumstances. But there are some things that we do not necessarily think about, but that are actually occurring. And one is an eddy current loss, or a heat loss, or hysteresis. And that is loss because the voltage is applied in a nonlinear fashion to the core. But just know, for the sake of understanding, those two things happen, but in the X-ray circuit, sometimes we have a transformer that needs to increase or decrease the voltage, and in others it may be used to increase or decrease the current. The three work together, but it's the transformer that we need to worry about, and when we get to the actual X-ray circuit, you're going to say, oh, well, that makes sense now, because we're going to step up or step down, and then we're going to talk about another type of transformer. Okay, so they all work together. Now that we've gone there, let's look at the equation units. So from here on out, we're going to talk about a relationship, V equals IR. Well, that's Ohm's law, and that has to do with intensity and or current and resistance. Now let's talk about transformer laws, and not the transformers that has honeybee, or bee is just a bee. He's my favorite of the transformers. That's all beside the point. Okay, so transformer laws for voltage and current are as follows. So anytime you see V, that is for the voltage, and I is the current, and we already know that. N is the number of turns. So when we talk about a transformer, it's constantly turning to create either voltage or current. Now, along with these large, and they're going to be capitalized, the P and the S, and they're like subscript, they're down below. P is for primary, S is for secondary, or you could say old and new, but we also just say primary and secondary. Okay, and these are the primary coils and the secondary coils. Here's the equation. The direct relationship and the transformer law for voltage is if, and you can either do it this way, so secondary voltage over primary voltage is equal to secondary turns over primary turns. I like flipping it this way, and I know our little s gets kind of down here, but this is very similar to the direct square law, because it's secondary over primary, secondary over primary. They're a direct relationship. So direct means if you have more turns, you're going to have more voltage. Less turns, less voltage. If you were given this equation, and you may very well be given this, here's an example. A transformer has 10 turns in the primary, 50 turns in the secondary, and 110 volts is applied. So what is the output? So your 110 is going to be your primary, and you're looking for your secondary. So you have Vs over Vp, Ns over Np, cross multiply, secondary voltage times 10 is equal to 50 times 110, which is 5,550. Divide both sides by 10 to leave this by itself, so your secondary voltage is 550. So 10 turns in the primary, 50 in the second, and you started out with 110 volts. Now, could you just say 10 divided into 50 is 5, so you've got 5 times more power? Yes, that would work, as long as you understood that, because that is, go back to this one, it is a direct relationship. More turns, more power. Here, more turns, more power. We started with 110, and now we have 550. Direct relationship. Now, if a transformer is supplied with 500 volts to the primary, 500 volts in the primary, 200 turns in the primary, and 40,000 turns in the secondary, what will be the voltage? So I did it this way this time. So again, secondary volts over primary, secondary turns over primary. Vs over 500, because that's our primary. Here's our secondary. There's our primary. And cross multiply, so you have Vs 200 is 500 times 40,000. Then it's 20 million. Divide by 200, and your answer is 100,000 volts, or you could say 100 kV. So it depends on what you want to do. But this was 500 volts. We went to 100,000 volts, but you could break it down to 100 kV. Just remember, anytime you see that K, there's going to be 1,000 in front of it. But we went from 200 into 40,000. Yep, you could divide that into that and see what your answer is. But we also know it should be more. So we went from 500 volts to 100,000 volts because it's a direct relationship. I can't emphasize enough, that's your most important thing, is that it's a direct relationship. Now, what if you want to find out the current? Remember, a transformer can either increase or decrease voltage or increase or decrease current. So a current equation with your transformer is inverse. So this would be similar to your inverse square law. So here we have secondary over primary, primary over secondary. So these are flipped, and it has an inverse relationship. So that in itself should mean if I have current and I increase my number of turns, your current should decrease because it's inversely related. So if a transformer has 10 turns in the primary, 50 turns in the secondary, and 5 amps is applied, what is the output current? So if you use that formula, IS over IP, NP over NS, then you have IS over 5, 10 over 50, IS cross multiply is 50, 50, now 1. So we started with 5 amps and now we're down to 1 because we increased the number of turns in the transformer. Inverse relationship. Let's do one more. So here is, we only did one problem for that. Now you need to see the voltage to the current. Now look at this one. We're now saying this is also an inverse relationship. If we change our voltage, then the current's going to change in an inverse proportion. So this is secondary current over primary current, primary voltage over secondary voltage. Inverse relationship. So a transformer has an input voltage of 110 and an input current of 5 amps. output voltage of 550. What is the output current? So we put our formula here, we cross multiply, and again, it's 1. So we started out with 5 amps, and there you go. Remember, this is the current and inverse relationship with the transformer. Now, current to voltage is also inversely. Again, 15% rule. If I increase my kV, I have to decrease my mass. So this is kV and mass. They are inversely related. And we've already done that problem. All right. The example presented with the explanation of electromagnetic mutual induction, we talked about this earlier, that's the simplest transformer design, consisting of 2 coils placed next to each other with one connected to an alternating current. When the alternating current is flowing through the primary coil, it has a fluctuating magnetic field, and this collapsing and expanding field induces electricity into the second coil, okay? The difference in the voltage induced in the secondary coil depends on the ratio of the number of turns. So these are turns that it's moving. For example, if there's twice as many turns in the secondary as in the primary, then the voltage is twice that. But if there are half as many, the voltage is half as many. But only the voltage and the turns have a direct relationship. The current is going to have an inverse, and then when you compare your current to your voltage, they also have an inverse relationship. So, much more sophisticated designs are used in X-ray, and we have what's called a closed core transformer and a shell type transformer. And they incorporate a ferromagnetic core to maximize efficiency. So this here is iron, ferromagnetic. There's not any problems or anything else that you need to do with it, except know that if it's closed core, the primary and secondary coils are separate from one another, and if it's a shell type, they intermingle. That's all you need to know about that, because now we get to move right into the auto transformer. All right, the auto transformer. One final type of transformer important to the X-ray machine is the auto transformer. This transformer operates on the principle of self-induction, and we talked about self-induction earlier. So know the difference between self-induction and mutual induction. This transformer has only one coil of wire around a central magnetic core, but don't think of it as the shell type. That has 2 coils of wire. So it's one coil of wire around a core, and the coil is used as both primary and secondary coils. Okay? And that's what we're talking about right here. This is the auto transformer. Now I'm jumping into something because this is what we're going to study next, but you need to understand how it starts with this auto transformer. This coil is used both as the primary and the secondary coil, and the outside wires are attached as different points along the coil, and the induced voltage varies depending on where the connections are made. So this is in your text. This is an image of the auto transformer, and this is what we're going to be studying when we start looking at the X-ray circuit. So very quickly, I want to recap because this is where I intended to stop halfway between the presentation, but the first part of it, I had gone so long, I didn't want y'all to have to listen to everything. So now we've gone into 3 different sections, and one of the main things that we've talked about in the first section was electricity. Then I brought you into magnetic, then the electromagnetism together. So think about all these things, and hold on just a second. So far we have covered the nature of electricity. So go back, write down whatever definition is that you can and so you'll remember electrostatics, electrodynamics. We've talked about electric potential, which is the volt, the current, which is the MA or the ampere, and then resistance, which is an ohm. We've talked about conductors And insulators, we've given examples, and then we've identified the devices that are important, electronic devices. Remember that whole list about batteries and resistors and all those good things. Make sure you understand those. And then we have a basic understanding of magnetism and then electromagnetism. And then we've talked about electromagnetic induction, both mutual and self. And then we've described basic generators, motors, and transformers. Now, I'm going to just stop this one just so that you're going to now have 3 sections, and I apologize for that, but that's better than having to listen to me for 2 hours straight. In the next section, though, we're going to talk about the X-ray circuit and its primary circuits, okay? So, let me stop this one, and I'll see y'all again in just a little bit.